Okay, so this is the Dijkstra algorithm, the idea behind the Dijkstra algorithm and why it is correct. Okay, so this is so far the outline of the algorithm. Okay, but this is not yet an implementation. This is not yet a code. Okay, so let's see now how we implement this idea. Okay, again, what do we need to do? These are all standard. Okay, and then we're going to maintain a set C for all the nodes that we already visited. We already figure out the shortest path correctly. Okay. Now, what do we need to implement? We need to first check how we're going to figure out whether we have to a way to maintain nodes outside C. Okay, that's number one. Number two, we also want to be able to retrieve from this outside nodes. We want to retrieve the one whose estimated distance is smallest. Okay, and then we can add it to the set C and then do the explore update operation. Okay, for all its neighbor. Okay, so those two we already know what to do. Okay, so we need to see how to implement this, and we need to see how to implement this. Okay, well, this sounds simple enough. Okay, so the most straightforward, the simplest approach is that, okay, I'm going to maintain the nodes outside, also use either a set or array. Okay, a set is better because later I need to remove it from the set, so it's easier with deletion. Okay, so that's what I'm going to do. I'm simply, so we have to implement this too. So I'm simply going to use another set to maintain the all the nodes outside C. Okay, now I'm not, note that here I didn't maintain C explicitly, because anything that's not outside is inside. Okay, so I didn't, so C is just the complement of outside. Okay, so C equal to your node set minus the outside. Okay, all right. So I'm going to now use a set to maintain all the outside nodes and to check. And every time I just check whether the outside is empty or not. It's empty, there's no more nodes. We'll finish exploring the entire graph. Otherwise, we continue to take notes, continue to run the while loop. Okay, so that's number one. Number two, we have to find the smallest nodes, the nodes with the smallest distance estimate, right? Okay, I can just use a linear scan, linear search. That's easiest way to find a min and a max, right? So I'm simply going to, we talked about this before, I'm simply going to use the linear search to find the minimum of the of all the nodes inside outside, where the key we're using the estimated distance. Okay, and then after that I remove this one from my set. Okay, I delete this node from outside because now it's added, so this is equivalent. C add is equivalent to adding this node to set C. Okay, it's the same. Okay, all right. Then this is same as before. We explore this new node we added by checking all its neighbors, see whether we can reach them through a faster way through edge UV now. Okay, that's it. Okay, so this is the entire algorithm. Okay, all you need to do is that you just need to have a procedure, which is this linear search for implementing the minimum, and then it's a complete algorithm. Okay, all right. So this is one implementation, and what is the time complexity of this algorithm? Okay, so this set at the beginning, it has, so to look at the time complexity, we have to see that what is the time complexity we need inside each iteration and how many iterations we need. Okay, how many iterations does the while loop run? What do you think? Well, we have to visit all the nodes. So the outside starts with all the graph nodes, and then each time we remove one from outside and add it to C. And we have to do this V times so that the outside become empty, so that we reach, we basically process all the outside nodes. Okay, so this number of iterations, so while loop runs exactly V iterations. Okay, in particular, each node will be removed, processed exactly once. Okay, the node will be removed from the outside once, and then that's a time we're also going to explore the neighbor of this. Okay, that's the first thing. Okay, so the while loop runs in V iterations. Okay. All right. Second, let's see. Inside, how long does this one take? Well, since I'm doing a linear search, so this step takes time proportional to the size of the outside, this array, right? And I know that this array essentially starts with size V and gradually reduce till V minus 1, V minus 2, V minus 3, and so on. Okay, so in other words, I can simplify to write this as the order big O of V because it's most of V. Okay, you can make this more precise. Okay, and I also have this. Well, this update operation only takes constant time. Okay, and this step takes exactly the degree of U. Note that when I write degree, it's a degree of U in the undirected graph, but for directed graph, this is number of neighbors, so it should really be outer degree for directed graph. Okay, I'm just simply writing the degree here. Okay, so basically you need the number of neighbors. Okay, so this step takes degree of U. Okay, what is the total time complexity? Well, the total time complexity, is the following. Okay, so this step, the line 10, basically, you have to run this one V times, okay? And each time you take time order of V. So essentially, it turned out that we need the V squared, okay? So V times V, okay? And you may say that, well, the size of this keep decreasing. First it was V, then it was V minus 1. So you can be more precise. So the line 10 total time really should be constant times V plus constant times V minus 1 plus V minus 2 tills 1. Because I mean, the size is basically going from the size of this array outside, going from V to V minus 1 and so on till 1. But this is just arithmetic series, and this is still giving me big theta of V squared. Okay? Or it's okay that if you understand this by, okay, this step takes at most V times, and this step has to be executed V times. That's why that order of V squared is a big O of V squared. It's an easy bound to get. Okay, turn out that it's actually also type, so it's big theta of V squared. Okay, so that's the time for line 10. Okay, all right. What is the time for this portion? Well, here, the total time for line 12 to 14 . So total time for lines 12 to 14. Here, basically, when I explore node U, I have to take time degree of U. Okay? And note that each U node can only be processed exactly once. That's when we remove it from the outside, when we take from outside to inside. Okay? In other words, we're going to sum it up for all nodes. Each node will be processed exactly once. Okay, so this is the total cost. And what's the sum of degree? Well, the sum of degree is 2 times E for undirected graph. And or if it's directed graph, we really should write out degree of U because this is the number of neighbors. Okay, and the total sum of out degree of U is exactly E for directed graph. But doesn't matter, in both cases, this is order E. Okay, so putting everything together, okay, so now if you put everything together, I'm going to just put it here. So this is basically what I just said. Putting everything together, we have that the time complexity, this is the order of E, sorry. Oh no, this is not the total, sorry. So it should be the total time complexity as such becomes order of V squared plus order of E, okay? But order of E, we know that the E is always at most V squared, okay? So that's why that this together is order of V squared. That's our time complexity for this naive implementation, okay? All right, I'm not going to spend more time on this because this is not the best way to implement this algorithm. We see that this one takes basically quadratic time in terms of number of nodes because every time, why? Because every time we have to perform a linear scan. So this is the bottleneck. This step takes time linear, and I will have to do this step V times. That's why we have V squared. So that's where the bottleneck of time complexity is, okay? So the question is that, can we do better? Okay, well, if you think about it, we are repeatedly performing linear scan to find the node outside with smallest distance estimate. Okay, every time when I'm in the new round, I again scan all the outside node and find the smallest. Okay, so that sounds like that we have a lot of redundancy there. We keep rechecking those outside again and again. Okay, so we want a data structure that can do the following. We want to be able to, for all the outside nodes, maintain the estimated distance, okay? And we want to be able to retrieve, extract efficiently the node with the minimum estimated distance, okay? And also, remember that in our code, after we take a new node U, when we explore it, we may update this estimated distance, okay? In particular, we have to update the estimated distance for a given node. In fact, since we only update it when we find a better distance, so we only decrease the estimated distance, okay? So we're asking now, do I have a data structure to do this? Because this is what the algorithm needs, okay? So do we have a data structure to do this more efficiently than what we did earlier using a set representation and then perform linear scan, okay? And it turned out that this operation is exactly what a standard so-called priority queue data structure is good for, okay? So what is the priority queue? You probably already seen this in DSC30, okay? It's basically a data structure that allows us to store basically a key for a node and the value pairs, okay? Key is used to identify this node, okay? And the value is some value that we're maintaining, okay? So, and this priority queue allows us to maintain such pairs and allow us to extract the key with the smallest, the lowest value, and also will allow us to update the value by decreasing it. And this is exactly what we need, okay? So priority queue itself as a data structure has many uses. I mean, for example, in the CPU do scheduling of jobs. I mean, usually the key is the ID of the job, and the value is how important is that the job, and then the CPU would then pick always the most important job to execute first. Okay, so there you maintain you want to pick the largest. Here we're talking about smallest, but it's the same. Okay, all right. So now assume that we're given this data structure. Okay, so in the Python package that we give you, this would be there. So suppose we're given this data structure. We're not going to discuss this data structure in detail in this class. Okay, as presumably you see in the other class as well. So let's assume that this priority queue class this is just the initialization, okay? And it can support the extract min operation. It removes and returns the key with smallest value, okay? And it also let us to update the value, okay, to a different one, okay? So suppose we now have this, okay? All right. In practice, how is priority queue implemented? Well, okay, we're going to talk about it in a minute. Here's just some example of showing what the priority queue is doing. Okay, so let's say that I initialize the priority queue to be the following pairs. There are 4 elements. They are the pair key W with value 5, key X with value 4, key Y with value 1, key Z with value 3. So now if I perform a query, it says that extract the min in this priority queue. What does it mean? That means that I need to look at here, find the one with the smallest value, and that's this one. That's the smallest value 1, and then I need to return the key. And I also extracted the note that this means that I'm going to remove it. Okay, so after this, my PQ will no longer have this entry. There are only 3 entries after this extract min operation. Okay, Now suppose I continue to perform change priority operation, which I'm changing the priority for W, which used to have key value 5. Now I change that one to be 2. Okay, suppose I perform this 2. Now if I perform extract min again, what should I return? Should I return Y? No, right? Exactly. Because Y is already not there. So now I have to look at the remainder, find the one with smallest value. And the remainder now with smallest value is actually W, because we already changed the value to be 2. Okay, so now we simply return W. That's what we have. Okay, so this is the priority queue. All right. Now in practice, priority queue is very easy to implement. Okay, one of the simplest way to implement a priority queue is using something called a heap data structure, a min heap. Okay, the heap data structure ultimately essentially just an array, very easy to maintain. Okay, so and using min heap implementation, which is what we're going to use for our Dijkstra algorithm. Okay, the initialization takes time linear to the size of the array of the set that you are initializing, the size of the priority queue. Okay, and extract min operation takes log n time, where n is the size of the current priority queue. So currently you have n elements in your priority queue. Okay, then extract the minimum only take logarithmic time, which is very efficient. Okay, and the change priority also take only log n time, where n the size of your priority queue. Okay, so this is using min heap implementation. This is the time we need for each of this operation. Okay, so all right, and with this, let's look at our algorithm again. So this is a Dijkstra algorithm using priority queue. Okay, so now for the outside, I'm going to use a priority queue. This is equivalent to my outside. Okay, at the beginning, I basically give all the nodes basically the value is infinity. Okay, so as long as this is not empty, I basically extract the smallest one, get the node with the smallest value, which is smallest estimate distance. Okay, then we do the same. We say that for all the graph, all the neighbors of B, we perform the update operation. Okay, I have to modify here one thing, which is that when we do the update, if we change the estimate, we also have to change the corresponding value in the priority queue for node V. Okay, so we remember that when we implement the update would return true if the estimate changes, otherwise it return false. Okay, so if change become true, namely we did update, we found a better way to reach V. Okay, then we have to update the value of node V inside my priority queue. Okay, so this is what the change priority is doing. So this is different from earlier, because earlier we're just using estimate to check for the estimate. Now I have to maintain the inside priority queue. So this one we didn't have before. Okay, all right, so this is the entire algorithm. Everything else remains the same. All right, okay, so so this is the major changes. Okay, so the first two is just how we maintain the outside and using the extract min operation to get the minimum. The last one is that now, since we also maintain a copy of the estimate as value inside the priority queue, we have to update this after the estimate change. That's it. Okay, all right, so what is the time complexity? Okay, so time complexity, first creating the priority queue, that is this step, this creating it, we said that, sorry, this is the step. This takes only proportional to the size of the priority queue, which is the order of V. Okay, so that's what we have here. So that's order of V for creating the priority queue. Okay, next we have the extract min. Okay, now first, how many times are we going to run extract min? Well, we basically, every node will be retrieved from outside at some point. So each node will be extracted exactly once. Okay, and once we extract it and then process it, check its neighbor, we're done with this node. We'll not touch it again. Okay, so we're going to perform this line exactly V times, the same as the size of the number of nodes. Okay, so this step will be executed exactly V times. Okay, what is the total cost then? Well, we said earlier that the cost of the priority queue extract min takes log of the size of the priority queue, okay? And the size at the beginning is V, so the cost of this one, the time is basically order of log V, okay? So it starts with log V and it gets smaller and smaller, but at the beginning, it's in fact a big theta of log V, okay? So when you sum up this V times, the total cost of the step is basically V log V, okay? All right, so this is what we have. And then, so now we talk about the cost for this, okay? And now let's see that how many times is this one going to be executed and what's the time complexity? Well, this one will be executed for every node U. This one will only be executed for at most degree of U times, right? So only for each neighbor of U, we potentially perform this step, right? So the step will be executed at most degree U of time, okay? And what is the time complexity? Again, degree means that our degree for direct graph, okay? But then what is the, so the total number of this, total number of calls to this procedure is basically we sum up all the nodes and sum up their degree, okay? So this gives us, as we said, is order of E, okay? Now, the total cost of the change priority, so here I should be more precise using big O because, I mean, maybe smaller than the edges, okay? So the total cost of this calling this procedure is basically the total number, and each time you take a log of V time for each of the change priority operation, okay? So total time complexity as such is big O. So let's sum everything up. So total time complexity is first initialization takes time order of V, and the total cost of extract min takes V log V, and the total cost of a change priority is E log V. So the total time is big O of V log V plus E log V, which is big O of V plus E log E. So this is time complexity of Dijkstra algorithm, okay? Note that I cannot just throw away V or throw away E because we don't know which one is bigger in general given the graph, okay? So I have to keep both of them, okay? If we know the graph is connected, for example, then you know that if a graph is connected, there are at least the V number of edges to touch all the nodes, okay? In which case you can change the time complexity. So you can write, sometimes you see people write Dijkstra running time is E log V, which is for connected graph. Okay, so so for connected graph, E is bigger than B minus 1, which means that order of, which means that the V is order of. Okay, so we're going to see this more clearly when we talk about spanning tree in the next lecture. Okay, all right, but bottom line is that if we use heap implementation for priority queue, then this algorithm is much more efficient because now we don't have to spend, see the bottleneck, the linear time to search for the minimum estimated distance now is replaced by extract min operation, which can be done in log V instead of V time. So it's a big improvement, okay? And as a result, the total time complexity now becomes V plus E times log V, which is better than the naive implementation earlier, okay? All right, let me just comment that one can actually also using the so-called Fibonacci Heat, which is a much fancier way to implement a priority queue, okay? So Fibonacci Heat is more complicated, but it also has a more better amortized performance than the standard heap implementation of heap, okay? And we use Fibonacci Heat because it improves on the priority queue operation. We can actually improve the time complexity to be E plus V log V. So what's the difference? Just now we said that it's E log V plus V log V, okay? So if E is dominating, here is E, here is E times log V. So this is definitely better, okay? So it can further improve the time complexity, okay? And okay, so that's basically what I want to talk about today. Again, I'm sorry that I went a bit longer today, but remember that the midterm will basically cover everything from hash table till today's class. Okay, the bottom line of shortest path algorithm is that for the weighted graph is that Bellman thought, which works for arbitrary graph, can be implemented in B times C time, and using Dijkstra for positively weighted graph. This is the running time we have for Dijkstra, which can be further improved if you use fancier data structure, but this is good enough, okay? And if the graph is unweighted, okay, or if all edges have the same weights, then what we talked about earlier, the breadth first search works, which led us to find the shortest path for one unweighted graph in time V plus E. So clearly, if my graph is unweighted, I can find shortest path more efficiently, V plus E. But if there's weight, you have to pay an extra log V factor. Okay, this is not surprising though. Okay, so this is the same as size of the graph, but if your graph has weights, you have to do a bit more to maintain the shortest one. So that gives you an extra log V factor for positively weighted graph. Okay, all right, that's all for today, and we'll send out the email about the return.